Hey there, folks. Here's a special problem that I wanted to cover today. Instead of a regular block sliding down a ramp problem, which we've done plenty of already, how about we try our luck against a much more challenging situation? Here, we have a block sliding down a wedge, and not only will the block move, but the wedge that it's resting on will move too. Let's begin with the free body diagram of that wedge. First, we'll draw the coordinate axes along the center portion of the wedge. Our vectors in the y direction acting on this object involve the wedge's weight and the normal force from the tabletop. These will be equal in length and opposite in direction, since the wedge will only move sideways. We also need to account for the normal force, or reaction force, of the block acting on the wedge as it slides down, so let's include that and label it capital R to separate it from the other normal vector. This will act at the same angle as alpha, so let's insert that and break R into the cosine and sine components. As you can see from the R vector, the block is going to push down and to the left on the wedge as it slides. This will cause the wedge itself to move to the left, which we'll account for by including a capital A acceleration vector pointing in that direction. Let's switch over to the free body diagram of the block. Here I've switched our coordinate axes to be parallel and perpendicular to the wedge, with plus x acting down the ramp. Along the y direction, we have the block's weight pointing straight down, as well as the reaction force again due to Newton's third law. Now, there's a couple ways that you can do this problem, but personally I find it easiest if we use the concept of fictitious forces. If we put ourselves in the accelerating frame of the block as it slides down, we can say that it will feel a fictitious force in response to the wedge sliding to the left underneath it. Let's give this fictitious force a special kind of vector to differentiate it from the other forces acting on the block, like this. Both the weight vector and this fictitious force act at angle alpha, so we can include that here as well, and grab our vector components for both vectors, like this. Let's also include an acceleration vector off to the side for the block. With that done, we can proceed to the sum of forces acting on the wedge. In the x direction, there's only the sine component of the reaction force acting to the left, and that's what's responsible for the wedge accelerating in the left direction. So since we have a negative on both sides here, we can toss those away and work with positive magnitudes. In the end, we'll just have to specify which direction these vectors are acting in. In the y direction, we have a couple terms showing up, but they all cancel each other out, since the wedge doesn't move up or down relative to the tabletop. Since our x sum here doesn't include the normal force of the wedge or, anything like that, the y sum down here is pretty much useless and we can ignore it. Let's just grab this x sum and call that equation number 1 for now, since that sum has this capital A acceleration that we need to solve for in it. For the block, our x sum will have contributions from the weight and the fictitious force that we included, and we can also exchange the weight term with mg and remove the mass entirely from everything here, because there's an m in all terms on both sides. In the y direction, we can do the same thing by exchanging the weight with mg again, Let's also move this third term over to the right-hand side, like this. It'll come in handy soon, as you'll see. And that's it for our sums. So let's grab our final equations in x and y and label those equation number 2 and 3. Let's take all three of those equations and bring them forward. As you can probably tell, there's going to be some algebra involved because there's 3 equations and 3 unknowns. So let's start with equation number 1 and try to solve for the wedge's acceleration, capital A. If we divide both sides by the sine of alpha, we can get an equation for this reaction force. I'm going to take this result and plug it into our third equation, since that has r in it. When we do that, we'll get the following. Since we want an expression for capital A, we should get rid of this denominator here in the first term by multiplying everything by the sine of alpha, like this. Now we're safe to factor out capital A on the left and divide both sides by what's in the parentheses on the left, like this. So now this is our expression for the wedge's acceleration, which acts to the left. To finish up part A, we need the components of the block's acceleration. Let's get the magnitude of that vector first, since we can't break it down into components without knowing what it is. Here's what we had for equation number 2. Since we know the expression for capital A here, we can plug that in, which will give us the following. Let's absorb this cosine of alpha piece hanging on outside into the parentheses. Notice that both terms on the left here contain a g sine of alpha portion. Okay, here's one, and g sine of alpha, there's the second. Let's just factor that out for our next step. Now we can do some cleanup by getting a common denominator inside the parentheses. I'll exchange this 1 with a special form of 1, which is modeled after what we see in the denominator of the other term here. Okay, so it's just that term divided by the same thing, which gives us that special form of 1. There's the same stuff in the downstairs of the terms in the parentheses now, so let's just unite them. Notice something a little familiar here. There's the same block mass, lowercase m, multiplied by sine squared of alpha and cosine squared of alpha, which means that we can factor lowercase m out like this. Since sine squared plus cosine squared is just 1, well, let's get rid of that inner parentheses term like this. Here's the magnitude of the acceleration of the block. Careful though, this isn't what part A is asking for. We're just going to use this to get to the components. Let's start with the x component. Instead of a simple a cosine alpha, we have to include the effect of the wedge's acceleration acting in the leftward direction. So if we plug in the expressions for capital and lowercase a, here's what the first line looks like. Next thing we can do is absorb this cosine alpha into the first term, like this. Following that, I'll distribute this g sine alpha cosine alpha term into the parentheses and end up with 3 terms, like this. Now it looks like we made things worse, but take a look at this. Our second term and third term are identical. One's just positive and the other is negative. I mean, yeah, sine and cosine are switched, but that doesn't matter. They are associative, so it doesn't matter what order they're in. They're still going to cancel each other out. Thus, our x component of the block's acceleration is just this first term here. That's it. Things are a bit easier in the y direction because the wedge doesn't accelerate up or down at all. Here, all we have to do is just slap a sine of alpha onto our lowercase a expression. I'll absorb the sine alphas together into a sine squared, and that's it. With the y component done too, part A is finished. In part B, we're asked to see if things reduce to the proper form when m becomes very large. In math language, that means we're going to take a limit of our accelerations from part A with capital M increasing to infinity. Let's see what happens to the acceleration of the wedge first. Here's a helpful reminder when it comes to the limit of quotients. The plan is to pass the limit into the numerator and denominator and apply them individually to get our answer. Let's try that. Upstairs, there's no capital M's to be found, so the numerator doesn't care in the slightest about m going to infinity. Well, capital M, mind you. It remains the same, just like this. Downstairs, we're free now to replace capital M with infinity and see what happens. It looks like we're adding a finite number here to infinity, which is still infinity. In fact, we can rewrite the entire denominator as such. If I have a finite number in the numerator, and the denominator just keeps getting larger and larger and larger, well, eventually the whole ratio is just going to go to 0. And that's exactly what we were looking for. If the wedge just keeps getting more and more massive, well, then it's not going to accelerate at all, which precisely describes the situation in our easier block and ramp problems. So far, so good. Let's see how it pans out with the block acceleration components. Taking the limit of the x component of the block's acceleration requires a slightly different approach. This time, we do have capital M in the numerator, so we can't just plug in infinity this time. This would result in an indeterminate form of infinity over infinity, which is not allowed. Instead, let's divide both the numerator and the denominator by capital M, like this. This will eliminate capital M from the numerator completely and change up our denominator a bit. Now that we have the same situation upstairs, where the numerator doesn't care in the slightest about m going to infinity, all we have to do is worry about applying the limit downstairs. At this point, we're free to plug infinity in now, so let's see what happens. Now the second term in the denominator will get smaller and smaller and smaller and fade away into nothing, which will leave us with just 1 in the denominator. Great. There's no need to leave the expression like this, because anything divided by 1 is just whatever you're dividing 1 by. So let's omit that 1 in the denominator and just report the numerator as our result. Does this agree with what we should expect? Yes. Let me tell you why. The acceleration vector of a regular block sliding down an incline, without considering components, is g times the sine of the angle. Notice we have that portion here, right? Our angle is theta, so we have g sine theta, or our angle is alpha, excuse me. So it's g sine alpha buried in this. Forgive me, I use alpha or theta way too much. Getting used to alpha. We're investigating the cosine component of this vector, which means we would expect an extra factor of cosine tagging along, which is exactly what this answer reduced to, right? Our expected portion plus an extra factor of cosine. So we're good. Now let's move on to the y component. When we plug this in, our first step that we can take is factoring out the g sine squared alpha coefficient in front of the limit. It doesn't contain capital M, so again, it doesn't care about the limit whatsoever. Like the last component, we can't plug infinity in right away because we'd end up with an indeterminate form of infinity over infinity. So to combat that, let's do the same trick of dividing the numerator and denominator by capital M. When we simplify, here's our result. And notice I've passed the limit in to act on both expressions, upstairs and downstairs. Okay, that's allowed now. Let's exchange capital M for infinity. And now we can sweep away the garbage that will just reduce to 0. In the end, we'll just be getting g sine squared alpha multiplied by 1 over 1, which is just 1. And we can omit the 1 and report the g sine squared alpha term. Let's do another sanity check just to be sure. Is this what we would expect? Well, yes, because g sine alpha is the regular vector of a block sliding down a ramp, but we're investigating the y component of it, so there's an extra sign tacked on and absorbed into the trig identity. That's all for part B. Now we need to show what the trajectory would look like. We've all seen the trajectory of a regular block sliding down a massive inclined plane. You know, it looks like this. And I've mentioned a couple times that the acceleration vector in that situation is g times the sine of the angle, in this case, alpha. But in this situation, we have the wedge underneath accelerating in the minus x direction while the block is moving. So by taking the vector sum of these two vectors, we'll get the actual path seen by an outside observer, which is just a straight line that's significantly steeper than g sine alpha, as shown by this new maroon colored one. But that's a bit vague for an answer, though. We can't use that as our result to part C. Let's do a bit of heavy lifting to prove what's being said here is true. The first thing on the list is to calculate what the slope would be. Let's begin by taking the ratio of the y and x components of the block's acceleration. We'll bring this g sine squared alpha term into the top parentheses and rewrite this whole thing as one giant ratio of ratios, like this. It's a bit ugly, I know, but notice the denominators in the upstairs ratio and the downstairs ratio, they're the same. So we can kill them off and evaluate what's left. Next, I'm going to do 2 steps in one, since they're pretty simple. Notice that we have a g in the numerator and the denominator, so those can be eliminated. Let's also distribute this sine squared alpha coefficient to both mass terms inside the parentheses, like that. We can break up this ratio into a sum of 2 ratios, and there's some additional canceling out that can be done here. I have capital M upstairs and downstairs in the first term, so that can be removed. Additionally, there's a sine term upstairs and downstairs in both of these, which means that they should reduce to the following. Both terms now contain sine over cosine, which is our familiar buddy, tangent. The only thing is, there's this mass ratio attached to the second term. That's okay though. We can factor it out of the second term like this. Let's switch in tangent and see what things look like from here. If we factor out tangent of alpha from both terms, we'll arrive at our final answer for our slope, this here. So if we go the extra mile and graph this situation, well, we better end up with this as a result for the value of the slope. Let's verify using our kinematic equations and Excel. Here's our displacement equation in both x and y, which we've used plenty of times before. Let's get rid of some things that we don't need here. There's no initial displacement in the x direction, so x sub I is just 0. Additionally, we were told that everything was at rest in the beginning, so the v initial times t terms, which should have x and y on them, forgive me on that, those are both 0, so I guess it really doesn't matter. Here's what we'll end up with. One more adjustment before we start plugging things in. In Excel, functions are plotted with plus x to the right and plus I upwards. This is going to conflict with how we set up our coordinate system for the block, where we had plus y down the ramp. If we want our plot to look like an object sliding down an incline, we'll need to exchange the plus sign in this y equation with a negative sign. This does not change our answers, though. Don't get that confused. We are only exchanging this sign out in order to make the plot in Excel look nice. We're not overriding anything that we did in our previous coordinate system. For a non-moving wedge, here's what our displacement equations will look like. I've exchanged the a sub x and the a sub y acceleration variables with the expressions that we worked out earlier when we let the mass of the wedge, capital M, go to infinity. When the wedge is moving, we'll use the a sub x and a sub y acceleration components of the block that we solved for in the beginning instead. Now, for the moment of truth. Does the plot agree with our prediction? Using some sample numbers here, I think it does. In the bottom left corner, you can see that I've just fed some sample values into our equations. And it doesn't really matter what kind of numbers you pick down here. As long as you're consistent with the equations and that the block is heavier than the wedge. But what really matters is that the shape of the graph is the way it should be, right? The trajectory with the movable wedge should be significantly steeper than the trajectory with the non-moving wedge. One last thing to be sure. I've told Excel to give me the trend line of our trajectory with the movable wedge, okay? This down here. And I want to focus specifically on the value of the slope right here. It's negative because of our adjustments of the y position equation or displacement equation for Excel, which means that in our coordinate setup with plus y acting down the ramp, we should be getting a positive 6.3509 when we feed the same values for the angle and the masses of the wedge and the block into our slope equation. Let's give it a shot. Here's that equation that we calculated for the slope, and I'm going to enter in 30 degrees for angle alpha, 10 for lowercase m, and 1 for capital M, which is what I used for the Excel plot. Do we get 6.3509? We do. Our claim is verified, and we are done. Let's recap on the solution card. We saw that in part A, our capital A acceleration, which was the acceleration of the wedge, it had this value pointing to the left. When we investigated the block, we found these results for our acceleration components using the positive direction pointing down the ramp. In part B, we took the limit of these accelerations in part A with capital M, the mass of the wedge, blowing up to infinity, and found that they agreed with the expected results found in a regular block sliding down an incline scenario. Finally, for part C, we figured out what the slope would be of the trajectory of the block by checking the ratio of the acceleration components, and we verified that against a plot in Excel, where we had to adjust a term in the y displacement equation to negative temporarily to make things look nice in the graph. But remember, that didn't change anything that we did up here. Oof, that was a long one. Certainly a difficult challenge problem, but we live to fight another day. See you all in the next one. Take care, everybody.